Okay, hi. Here we're talking about a congestion algorithm called ECN, Explicit Congestion Notification. A series of congestion control algorithms were introduced in lectures before. There are mainly three problems that need to be solved about the congestion control. The first one is the problem of congestion judgment. The second problem is about the how to adjust the speed, and the third one is the problem of retransmission. Congestion judgment is that how the end system judges whether the network is congested. The speed adjustment is how to reduce the speed when there is congestion and how to increase the speed when there is no congestion. Retransmission is a problem of reliable data transmission. The algorithm of congestion control we introduced before mainly depends on the end system itself to judge whether there is a congestion, such as by timeout or the occurrence of three redundant acknowledgements. As long as as any of these two events occurred, the end system thinks that the network is congested and decrease the speed of data transmission. If neither of these two events occurs, it is considered that the network is not just congested and the speed will be increased. The network has no feedback information and will not tell the end system whether there is congestion. However, if the network can send some network congestion information to the end system, the feedback time will be shorter than the timeout or three redundant acknowledgements, and the efficiency of the congestion control can be better. This is the ECN algorithms we talk about today. The ECN algorithm can improve the performance of active queue management mechanism. For example, the RED algorithm randomly drops packets according to the queue length. With the use of ECN algorithm, there is no need to lose packets within a certain range. You only need to mark these packets. This marking information can explicitly send congestion information to the sender without waiting for the timeout or three repeated acknowledgements. Especially time-sensitive connection benefits from ECN, and many packet loss can be reduced by using this algorithm. Since the network needs to provide congestion information, the IP protocol and the TCP protocol must be modified accordingly, and some flag bits and fields needs to be added to carry some congestion information. So let's take a look at the modification of ECN to IP and the TCP protocol. First of all, for the IP protocol, in the initial flag bits of IP datagram, the highest two bits are used. The highest bit is called CE, congestion experience. This flag bit is used by the routers. If a datagram is received and the network is congested, this bit will be set to 1, which means that the congestion has been experienced when passing through this router. The other flag bit is called ECT, which is the flag bit for ECN enable. If the host is ECN enabled, it means that it supports ECN. When sending IP datagram, ECT needs to be set to 1. The combination of two flags of ECT and the CE is shown here. If the combination is 00, it means that the host do not support ECN. If they are 01 or 10, that means the same to the router, which means that the host that sends the IP datagram are ECN enabled. If the two bits are both 1, it means congestion occurs when passing through the network. The last part of the IP datagram is the IP payload, which can be a TCP segment or a UDP datagram. If it is a TCP segment, the lowest 2 bits of the segments are used. One is called CWR and another is called ECE. The ECE is ECN echo. It is set by the source host, the target host. When IP package arrives at the target host and the network is congested, the target host knows that the congestion has occurred through the feedback provided by the network. The target host should set the speed to 1 and send it to the source host. CWR is called congestion window reduce. It is set by the source host. When congestion occurs, the congestion window needs to be halved. After the sender reduces its congestion window, it will set CWR to 1, indicating that it has reduced the congestion window. Let's take a look at the working process of ECN algorithm. The two processes establish a TCP connection. The connection process is almost the same with the general TCP connection, except that there are some differences between the combination of the flag bits. In the establishment of the connection, the sender and the receiver needs to negotiate whether ECN can be used. The TCP segment sent by the source host forms an IP datagram. When passing through some router, the flag bits CE and the ECT of the datagram is either 10 or 01, indicating that the source host is ECN enabled. And here, the routers use a modified RED algorithm. The router can mark the bits instead of discarding the packet when congestion occurs. The modified router can set CE bit in the head of the IP datagram. If congestion occurs, both bits will be set to 1, telling the target host that the congestion has occurred. After the target host receives the IP datagram, it sets ECE bit to 1 in the TCP header to tell the source host that the network congestion has occurred. When the source host receives the segment, it needs to halve the congestion window and set CWR to 1 in the sent TCP segment to tell the target host that the speed has been slowed down. When the target host receives the segment with CWR equals to 1, it knows that the ECN message sent by it has been received, and the ECE flag will no longer need to be set to 1. When congestion occurs, all packets sent by the target host to the source host need to set the ECE bit to 1. The source host will receive a lot of segments with ECE equals to 1. It will slow down the speed of transmission and telling the target host about this slowdown information. For a series of message segments, the speed will not be reduced twice. The ECN mechanism can explicitly notify the sender of congestion. The sender of congestion without waiting for timeout retransmission or 3 repeated acknowledgements, which can improve the efficiency of congestion control. The ECN mechanism can avoid unnecessary package loss, does not require retransmission timeout, and does not rely on coarse-grained TCP timing. This effect is most obvious when the TCP connection has a single unfinished segment. It can avoid the transmission control protocol timeout. Since the ECN is only effective in conjunction with the active queue management strategies, the benefits of ECN depend on the accuracy of EQM. The use of ECN has been found harmful on highly congested networks, and the AQM algorithm prevents packets from being dropped. Modern AQM implementation will drop packets under extremely high loads instead of marking this package to avoid this situation. There are also security issues. If an attacker forces ECN to 1.1 when a datagram goes through some routers, the source host will continue to slow down the speed of transmission, resulting in a continuous decrease in throughput. The effect of ECN on batch throughput is not clear because the modern TCP implementation has a large enough window on the sender to deal with the loss of segments in time. ECN message could be dropped by the network before reaching the TCP source. For a TCP connection, package loss are a reliable indication of congestion, but for ECN, it makes source host believe that there's no congestion. And ECN algorithm has also many other deployment problems. And that is all about what I want to talk about ECN today. Thank you.